This video is part 1 of Chapter 5, Memory for PSY 110S, the Psychological Sciences. In this chapter, you're going to look at how psychologists have developed theories for helping them understand how memory works, the types of memory that have been identified, the ways in which we put information into memory, how we get it back out, why we forget stuff, and finally some of the fallibility of human memory, because human memory is imperfect, as I'm sure you know. We're going to start by looking at what's called the three-stage model of memory. In your textbook, this graphic helps to illustrate how the three-stage model is laid out. In the boxes on the model, you see sensory memory, which are also called registers, short-term or working memory, and then long-term memory. Then the model is laid out such that you have input that comes in through your sensory systems. If it's language, like if someone is speaking to you, you're hearing, but you're also looking at them, seeing them, and taking in a lot of information about what they're saying. The information is stored very, very briefly in the sensory memory, so the sight of the person who's speaking, the sound of their voice, all of those little elements are going to be briefly stored in the sensory memory. Then, if you're going to hold on to that, you need to encode it. That requires that you give it some attention, that you recognize what's happening, and you use your short-term memory in order to work with that information. That's why it's called working memory, to put it in a form where it can be, if it's important enough or useful enough, placed in long-term memory. Once it's in long-term memory, you can pull it back out, and that's what the word retrieval refers to in the model. At any stage, if you don't pay enough attention, if you don't use the information rapidly, or connect it to other kinds of information, that's when forgetting occurs. Let's look at each of these aspects of the three-stage model separately. First, the sensory memory. Sensory memory is described as having 5 quote-unquote registers. I think they're using that language to describe sensory memory because it's very fleeting. It's like the sensory system registers the input of new information. It's only going to last a very short period of time. The 5 registers are associated with our senses, so sight, hearing, taste, smell, and touch. What this is used for is it's a brief repository of incoming sensory data from the physical environment. If we pay attention to it, like there's a whole lot of sensory information around me, even sitting in this relatively quiet room, that unless I pay attention to it, I'm not even consciously aware it's there. So the first thing you have to do in order to remember something is pay attention to it. Once you've paid attention to it, recognized its significance, then it can move on. In terms of research on sensory memory, most of the research has been done with sight and hearing. As I talked about in the sensation and perception chapter, those are our dominant senses, so we tend to have focused more research and attention on those areas. Iconic memory is basically the visual sensory memory system. Iconic, if you break the word down, icons, so images, these are exact copies of information in your iconic memory. So one example that I would use when I would study my notes, so I would take notes either on a book or notes from class, and as I was studying for exams when I was in college, one of the iconic traces would be where on the page a particular piece of information lay, and I would have that image of that place on the page as an iconic trace. You're also, one way of testing your iconic memory is to turn around wherever you are right now, briefly look at the scene and then turn back. There will be an iconic register of what was there. Unless you give it greater attention and organize your use of that information, you have less than a second, and that image is going to fade. The visual information that we attend to is going to get reorganized. So it's going to be processed to the point where it can then move to short-term memory. So, classic example, if I look at a phone number, we used to, back in my day, have phone books, but let's say I'm online and I'm looking up a business phone number. I'm trying to remember it. In iconic memory, there is the literal image of the numbers on the screen. If I want it to go to short-term memory and hold on to it long enough to use it, I'm going to have to do something with that information. First I'm going to have to recognize that it's a phone number and organize it as such. Then I'm going to have to rehearse it and keep it moving. Otherwise, it's just going to fade away very quickly. Information in long-term memory is going to be used. So if I see that phone number, I know what phone numbers are. I can, for instance, use top-down processing to ignore the area code. So let's say it's the same as my area code. That's not novel information. It's not necessary for me to pay any attention to it. So I'm using information from long-term memory to note that it's not necessary for me to rehearse the area code. It's the same one as mine. And then I would be able to work on the other stuff that I was seeing. This recognition process, using some of the top-down information to help us, can also, lead to some tricky errors that we might make, because we might assume connections that don't exist. And we'll talk about that a little bit next. But the recognition process that's involved in perception gives us the opportunity to encode the information that's currently in iconic memory into short-term memory. We can use some top-down processing in order to make that easier. That's why our phone numbers are organized in chunks. So you have 3 numbers, 4 numbers, for example. So when you look at these letters on the side here of this screen, this is one of the tests that we have, that researchers have to test iconic memory. So what would happen in the laboratory is you get a flash on the screen of these letters, and for a very, very brief period of time, you have an exact duplicate of that image in your mind. Most people in the Western world, in the U.S., we go left to right, top to bottom. So you're going to start automatically sort of processing those letters. Without an opportunity for rehearsal, you'll likely get very few of those letters sticking. Another procedure for understanding iconic memory is the temporal integration procedure. And here you've got, and this image comes from your textbook, you have a couple of meaningless dot patterns, which are A and B on this particular image, and they're shown sequentially, one after the other, in the same visual location. So the iconic trace, if they're shown fast enough, you have one. So image A would flash on, flash off, image B would flash on, flash off. If it happens fast enough, you have both iconic images present at the same time in the sensory register. Then what you get is a composite, and that is sort of represented by image C. So when the two meaningless patterns are integrated, a meaningful pattern emerges where you can detect the presence of letters amid the other dots. So what you see there is a VOH pattern seen. So this meaningful pattern can only happen if there is a leftover trace of A still in the sensory register when B is shown. And that overlay is going to be integrated into one image that is then perceived as meaningful. So once the meaningful pattern's recognized, that means that these two patterns had to have been overlapping and then integrated in the memory system. What happens to participants when they do this kind of task is that you're not seeing the meaningful pattern when the dots are separate, when the dot patterns A and B are separate. Instead, you have to overlay one over the other before you can see it. So essentially, the purpose of this is to show, is to test, A, is there an iconic leftover image still in the register, but also how long does it last? So for instance, they would vary the amount of exposure and then the delay between showing image B after the offset of image A, and that pretty much gives you the duration of the sensory trace. Now another method for looking at sensory memory is Sperling's approach, doing full and partial report procedures. In this type of setup, participants are going to be presented with 3x3 matrices of letters. So remember back a couple of slides ago when I showed you that 3x3 matrix of letters? That's what you're talking about here. So sets of 9 numbers. They're shown for 50 milliseconds across a number of trials. In the full report procedure, you have to report all 9 numbers. And participants are fully able to say they know that they saw 9 numbers. They saw the whole matrix. But by the time they could report all the numbers, the image fades. So they can only get through part of it. In the partial report procedure, participants only had to report one row at a time. And they could do this by cue. So say middle row, they can give that. Top row, they can give that. Bottom row, they can give that. Because it's still in the memory trace and they can go to it before it fades. An immediate, what can happen in some of these is with the prompted cue, when they're given an auditory cue, that can result in successful recall. If there's even as much as a 1 second delay, memory performance is much more poor. So you lose letters, you replace letters, and don't get them right. After the sensory memory, so if people pay attention and recognize what they are being exposed to through their sensory memory, then the information can be moved to short-term memory. So there's a bit of processing that occurs here to get the information into short-term memory. So go back to the example I gave of being online and looking up a phone number on my computer. Now, if it was on my phone, I would just push on the number and it would magically dial for me. But what if I have to remember it? So I see it on my screen. I maybe even say it out loud. It will get into the sensory trace. Now that I'm paying close attention to it, I want it to migrate to short-term memory. And I want to hold on to it long enough to punch in the numbers in my phone without looking at the screen. That requires short-term memory, which again is sometimes referred to as working memory. Whoops, sorry about that. In this memory stage, it requires a conscious effort to keep the information alive. Otherwise, if we get distracted, if we look at something else, if we do some other task, like an interference task, we stand a really, really solid chance of losing that information. So what you're doing a lot of the time in short-term memory is rehearsing. So repeating the information. Let's say I'm on the road, there's a car accident that I witness, and I am trying to memorize the license plate number because the car that caused the accident has just run off and I want to be able to tell someone. So in order to hold that information, I'm going to rehearse it until I have an opportunity to write it down. If I'm interrupted, if anything happens that gets in the way of me continuing to rehearse that information, I'm highly likely to lose it. Short-term memory has a pretty limited capacity. Some people are pretty gifted at manipulating that capacity, but for most of us with pretty regular, normal memory abilities, we can hold about 7 plus or minus 2 chunks of information. So go back to that phone number idea. The reason we chunk elements of the phone number is to make it easier to remember them. So you've got 3 numbers, 4 numbers, they're broken into pieces. And that allows us to chunk them so that we can remember them more efficiently and hold on to them longer. Now, short-term memory, on average, has brief duration, not nearly as brief as sensory memory, but on average about 30 seconds. Some individuals have extremely good short-term memory capacity as well as duration. Some people have good capacity but not necessarily strong duration. Some people have really good duration, issues with capacity. If you're talking about someone with extraordinary memory abilities, they tend to have both some expanded capacity, but more likely the ability to hyperchunk information. So large blocks of information can be chunked together, and then expanded duration. But for most of us, we're limited to 7 plus or minus 2, so 5 to 9 chunks of information, less than 30 seconds of time. When we're looking at the capacity, researchers use tasks like a memory span task in order to assess what's the capacity of human short-term memory. So they'll give people lists, lists of words, lists of letters, whatever. And that's how this 5 to 9 chunks of information range has been established. The task, typically done to test for the capacity of short-term memory, and just to bring this down to earth, if you have someone in your home who is experiencing some memory difficulties, chances are pretty good they're having problems with their short-term memory. So a neurologist might give the person a memory span task to test for the capacity of short-term memory, and then later they're going to test for duration as well, in order to compare that with a baseline or a benchmark to determine whether or not their memory is problematic. Chunks are basically any meaningful units of information. So, in our telephone numbers, we have area code, and then the second set of numbers is more closely to your region. Like I have, my area code is 330, which is one of several Northeast Ohio area codes, and then I have a Canton prefix, one of many, many Canton prefixes, and then the 4 numbers that are unique to my phone number. And those are chunks. They're meaningful units of information. I'm also thinking of my social security number. It's 324 are the size of the chunks, and over my working life I've had to memorize that and give it meaning. Now there are other ways that you can chunk information. If I give you a long list of words and they are a mixture of, say, fruits, vegetables, and grains, and they're all scrambled, what I might do to chunk them is create category lists. So all the fruits, all the vegetables, all the grains, and chunk them in that way to increase the likelihood that I'll remember the information. Now, to test the duration of short-term memory, what's often done is to create a situation where you have a distractor task. So you present the information that's to be remembered, and then there's an immediate distraction. So often what this involves is counting backwards by an odd number, like counting backwards by 3s, by 7s, not the easy one, 5s, that would be super easy, but count backwards by 3s or 7s from 100. That can be very challenging. It takes up a lot of energy for most people to do that task. That distraction takes away from any ability you have to rehearse information that's in short-term memory. And that's a way that we can tap into just how long can short-term memory last. The way you would lay this out in an experimental situation is you'd present the information, run the distractor, then do the recall test. You would typically have a control group. You have a control group that isn't exposed to the distractor task, but they're just allowed to continue rehearsing the information. And then you compare their recall scores. Maintenance rehearsal is what that control group will be doing. They're keeping that information alive in memory. So, let's say you've seen a car accident, you were the witness, and the one causing the accident ran off, but you saw their license plate. You can't find anything to write with, so you're just repeating the numbers from the license plate over and over and over again until you can find a way to put that in a more permanent place. Like writing it down or giving meaning to the letters and numbers that you've seen and connecting them to some previous amount of information or type of information and getting it to long-term memory. Now what your authors present to you is this image from your text of doing a short-term memory duration task. And what they're doing here is showing you across the bottom axis time in seconds between presenting the letters is the example that they're giving you in the text, and then this particular graph shows what happens when you increase the number of seconds where no rehearsal is allowed. So what you can see in the curve is basically if you prevent using a distractor task any kind of rehearsal, there is rapid loss of that newly presented information. It's highly likely that you will not remember it as a result. So what are we doing when we engage in maintenance rehearsal? So go back to that car crash. You really need to remember that license plate, but you don't have anything to write it down on. Maybe your phone isn't working, so you can't type it into notes or whatever. You need to remember it, and all you've got is your brain. So what you're going to do is repeat the information over and over in order to keep a hold of it. That's why we often call this working memory. You actively have to work with the information in order to keep it alive. Now you can, if you really want to encode this and keep it for long term, you have to work with the information in a more symbolic way. There are lots of little maintenance rehearsal tricks and techniques. Your authors describe several of them, like the phonological loop, which allows you to use verbal information for a short period of time where, say, you're repeating a phone number or a license plate number over and over in order to keep it alive. The visual spatial sketchpad involves keeping sort of a visual representation of the information that you're learning. So the example I gave early in the lecture was imagining where in my notes, like I'm having trouble remembering something that I studied, where in my notes, what did it look like on the page? Or if I'm trying to remember something from the textbook, was it the top of the page, the bottom of the page, were there images near it? That helps you to make connections using other sensory information that may trigger you to remember it. The episodic buffer is an idea that is part of the functioning of the working memory system, and it involves pulling information from the phonological loop and the visual spatial sketchpad and other information from your previous memory to integrate new information. So, if you're learning a relatively new concept, in class, maybe your teacher has a PowerPoint slide up there, and you're looking at it. So you're processing a lot of verbal input, you're processing sounds and visual images. You're going to use those visual spatial cues as well as what you're trying to rehearse phonologically in order to hold that information. The central executive component is where the coordination occurs. So there are a lot of separate activities that you need to be able to do in order to hold on to information and then use it later, either to move it to long-term memory or execute some sort of action. So the central executive component is designed to coordinate activities and distribute resources to the other three components, the phonological loop, the visual spatial sketchpad, and the episodic buffer. This processing is designed to help your memory work more efficiently. It can only be done, though, with attention, and distractions, other kinds of interference can derail any of that process. It can interfere with the phonological loop. It can interfere with your ability to kind of hold that visual spatial imagery in mind. It can wipe something out of the episodic buffer, and so on. So we can only hold stuff for as long as we can keep working with that information. Otherwise, it tends to be forgotten. That concludes part 1 of Chapter 5.